Hi, my name is Georgia Channing, and I am a senior at the University of Tennessee, Knoxville. My research focused on hyperspectral imaging and is entitled Spectral DefocusCam, a compressive hyperspectral imaging from defocus measurements. Before we delve in deeper to that, I just want to give a quick shout out to the people who supervised me at the University of California, Berkeley, Christina Monakova, Kyrillos Yanni, and Dr. Laura Waller. My research focused on democratizing hyperspectral imaging. So hyperspectral cameras are very fancy cameras that don't just take red, green, and blue values, but collect color values from all across the wavelength, the color spectrum. But most of these cameras are prohibitively expensive, particularly for places in the third world, oftentimes costing $20,000 or more a piece. So the goal of this project is to design a camera for about $10 that can mimic that behavior. And we propose to do that by making a tunable lens that can rapidly change focus paired with a 31-channel spectral filter array mounted on a CMOS camera. But this camera doesn't exist yet. So in order to build a reconstruction network, we had to simulate the camera's behavior as well. The way we did this was we took ground truth images, or what we took as ground truth, which were in fact real hyperspectral images from Harvard's real world spectral hyperspectral image database as the ground truth, as you can see in the lower left. And then we used a blurry PSF or point spread function and a sharp one to create simulated data with different amounts of defocus. We kind of took this then as the simulated camera data and went about trying to reconstruct it. So what that meant was I took the simulated data, fed it back through two different kinds of UNet architectures to get the whole hyperspectral volumes out on the other end. We tested 6 different models, some with noise and some without. And you can see here on the right, the results of different model combinations with loss measurements. And the best one that we trained without noise was the 2D UNet with L1 loss, and the best one with noise was the 3D UNet with L1 loss. This research is really exciting because it's one step closer to making really affordable hyperspectral cameras, which can be of invaluable worth in agriculture, medical applications, as well as a whole slew of applications that likely have not been discovered yet. In future research, I would try out more different models, as well as investigate a little more why LPIP's loss was not as fruitful as we hoped it might be. Thank you so much for listening, and come stop by and chat with me.